Okay, so part B has to do with magnetic fields and orienting the magnetic fields of a bar magnet. First, we're orienting it in the magnetic field of the Earth. So we're doing what's called the polarity check. So I have suspended a magnet from a piece of string. I let the magnet kind of settle out and point in a particular direction. So if you come zoom in on that magnet, you can see that the north pole of the magnet is pointing, and eventually it's going to settle in that direction. It's just been kind of waffling back and forth between that point and this point. And surprisingly, north is this way, which seems kind of counterintuitive. But in one of the dumbest decisions in scientific history, they decided to print an N on the end of the magnet that pointed north and call it north seeking, meaning it will seek the north pole of the Earth's magnetic field. However, if I take this N and interact it with another bar magnet, well, it does not stick to the north, it sticks to the south. So these magnets behave appropriately. This N, however, again, in the dumbest decision ever decided upon by scientific minds, the N means north-seeking, at least with reference to the Earth's magnetic field. During this section, we're going to be imaging the magnetic field of a bar magnet using iron filings. So I have a handful of iron filings, and then underneath here is a small bar magnet, and we're going to see the orientation of the bar magnetic field simply by sprinkling iron filings and then watching the magnet occur, or the magic occur rather. There you have it. So you can see it emanates out from the north back to the south, out from the north back to the south. Now what you can't see is that this magnetic field, this is a two-dimensional representation since the paper is two-dimensional. Over here I have a three-dimensional. So there's a cowl magnet inside of a test tube, and you can see the magnetic fields in more or less in 3 dimensions. Pause. Next section, we now have 2 north poles facing each other. So we can see the battle between those magnetic fields. Pause. Now we have north-south poles facing each other. And you can see, rather than duking it out, you can see the field lines going straight across. Going straight across there. And then circular here, and then now we have a piece of rectangular iron in between the north and south pole of opposing bar magnets. And we can see the soft iron acting as a magnet, a weak magnet. but it is nonetheless. You can see the outline of the piece of iron right here. Magnetic field going straight across, oppositely poled magnets. Now we have a circular, actually a washer made of iron in between the north and south poles of opposing magnets. So we can clearly see that the outer ring is magnetic, but the inner portion is not. So the field strength of the magnetic field in a circular conductor is nada. Pause. Now this lab is messing with magnets, so before I clean up this mess, it's cool to just woo. Oh, it's art. All right. All right, the last part of this section, well, second to last part, deals with compasses and their orientation in the magnetic field of a bar magnet. So if you just watch the compass as I move it, now we can replay that in slow motion simply by placing individual compasses. Would that be compi? Ta-da! Pause. The last section deals with two paper clips that are oriented, they're floating freely in petri dishes. Here's a bar magnet, and if I turn this one randomly, get it spinning, okay, versus this one, you can see that it behaves differently towards the different poles. And it will always orient with this end pointing north, because that's been magnetized. This one, however, well, it's behaving the same way. How can it be magnetic? I just got it out of my drawer. Pause. Okay, so we're getting unexpected results. We have an unmagnetized or seemingly unmagnetized, not compass, paperclip. That's it. It was out of the drawer in my room. I placed it in the water, and it keeps oriented in the same plane as this permanently magnetized paperclip. I had this aligned in the magnetic field of neodymium magnets since last year at this time. Now let's think about this. These are now compass needles, which are pointing north, which means that this is north-seeking end of the paperclip. And if I put another north-seeking end of a permanent bar magnet, what will happen? It repels. It repels. It repels both of them. If I bring the south pole, it attracts north to south, north to south. All right, pretty fun. Messing with magnets.